Okay, we're going to talk now about the elementary symmetric polynomials. And instead of starting with the general case, um, let's think about the case when n is equal to 2 first. So a general quadratic looks like f of t is t minus t1, t minus t2, where t1 and t2 are the roots, right? We can factor it over c. As long as the polynomial is defined over C, and it looks like that. Now, what happens when we multiply that out? Well, what we're going to get here is we're going to get t, and then what's t squared rather, and then what's the way we can get a linear term in t? Well, we have to do the out and the inside. So that's going to be minus t1 plus t2, and then our constant term is t1, t2. And notice that these expressions that show up in the coefficients, these are symmetric in the indices. That is, if we swap 1 and 2, then S1, S2 do not change, right? If we swap the 1 with the 2, if we interchange them, it's T2 plus T1, but that's the same thing as T1 plus T2. And similarly, if we swap the T1 and the 1 and 2 here, we get T2, T1, but that's the same as T1, T2. So the coefficients of the corresponding quadratic are symmetric polynomials in the roots. Okay, that's just me writing out because it's important to write out. So that's the case with n equals 2. Let's see what happens when n equals 3. So a general cubic is going to look like t minus t1, t minus t2, t minus t3. And if we multiply this out, we're going to get t squared minus t1 plus t2, t plus t1, t2, t minus t3. And then we're going to get t cubed. And let's see, how can we get a squared term? Well, we can multiply this t with this t, okay, and that's going to be t1 plus t2. But then we can also multiply this t squared with that constant, and that's a negative t3, but I'm going to bring it inside of the parentheses as a plus. And then what? How can we get a t term? Well, I can multiply this t with that guy, in which case the negatives are going to cancel, and we're going to get t3 times t1 plus t2. This is with a t. And we can also get a t by multiplying this constant with a t. So that's plus t1, t2. And then our constant term is, of course, minus t1, t2, t3. So let's look at those coefficients here. I'm going to set S1 to be the negative of the quadratic coefficient. S2 is going to be t1, t3, t2, t3, if we multiply that t3 in, plus t1, t2. And then S3 is going to be t1, t2, t3. I'm going to ignore the negative. So then F, of course, we can just rewrite it as t cubed minus s1t squared plus s2t minus s3. And notice again, the coefficients of the corresponding cubic are, well, what happens if we move around in S1? What happens if we swap 1 and 2? Well, we get the same thing, right? And what happens if we swap 2 and 3? We get the same thing. What happens if we cycle through 1, 2, and 3? We get the same thing. And the same thing here. What happens if we swap 1 and 3? Well, this guy is left alone if we swap 1 and 3. And these guys will interchange, right? Because the two will stay there, and the 1 and 3 will swap. So we'll swap these expressions. But S2 on its own is not changing. If we cycle through 1, 2, and 3, it will not change. And similarly here, if we do any sort of permutation of the indices, S3 will not change. So the coefficients of f are symmetric polynomials in the roots. And in general, we can write f of t, we can factor it over c as t minus t1, t minus t2, all the way to t minus tn. And when we multiply it out, we're going to get tn minus s1 t to the n minus 1 plus s2 t to the n minus 2, all the way down, well, I guess it's minus after that, minus all the way down, and then we get some plus or minus, well, the actual sign is negative 1 to the n Sn. So when n is odd, we get a negative number like we saw here, minus S3. And when n is even, we could have written f of t here as t squared minus S1t plus S2. We should get a positive. Okay? So it starts off negative and just alternates sign. That's the way to remember it. All right, where S1, what was S1 in the previous case? S1 was the sum of the 3 roots, and S1 was the sum of the 2 roots. So what should happen here? Well, we should get the sum of all n roots. S2, what was that? S2 in the first case was the product of the roots. In the second case was all pairwise products of the roots. And the same thing is going to be true here. It's going to be the sum on I less than j, ti, tj. Or we could write that out as t1, t2 plus t1, t3, all the way up to t1, tn, and then we go up to t2, t3, all the way up to t2, tn, and then we keep going until we get to tn minus 1, tn, which is just all pairwise, well, let me not say all, the sum of all pairwise products of the roots. All right, similarly, S3 is going to be the sum of all triple products, distinct triple products of the roots. And then finally, Sn is just the product of all the roots. And when we do this process of summing all possible products, we create a symmetric polynomial as well. So these are clearly going to be symmetric polynomials. Okay. All right. So that's a quick introduction to symmetric polynomials. They're very important.